Good afternoon, everybody. So I get to talk about what seems to be a very popular subject. And Doug's very kind with his words, but to be honest with you, I've learned about technology over the years couldn't have happened without all the guys at UE Systems, so I want to thank them for that to begin with. Yeah, I heard that. You know, my ears aren't failing yet. It's not the first thing to go when you get old. But he's right. I think I've only missed 2 conferences, and I love coming down here. There's a lot of familiar faces, a lot of new faces, so it's good to be back here in Clearwater. Start off giving you a little background about myself and what I do and how I'm involved with the electrical side. But I'm a maintenance electrician by trade. I spent over 20 years out in the field working my tools in a lot of different places, from the U.S. military to shipyards, chemical plants, phosphate mines, cogeneration facilities, steel mills, titanium mills, and the last 10 years I've been in my current capacity with a company called TEG Corporation out of Pittsburgh, Pennsylvania. And just by virtue of being with this company has really afforded me the opportunity to learn all this cool stuff that I've been doing for the last 10 years. Excuse me. The reason for that is we are a franchisor of electrical contractors all over the world. And we sell a business system and train and support independently owned contractors that really aren't used to doing the type of services that we talk about with regularity here. And, you know, your typical construction electrician, if you will, isn't used to the predictive mindset and things like that. So it's always culture shock to get them involved with these. And to give you an idea of our footprint in the world, currently here in North America, we've got about 95% of the major markets covered between the US and Canada. And we're currently in 22 different countries right now and growing. So there's a lot of organizations out there. I think we have 132 contractors in our network, and myself and my team are responsible for more than 500 technicians across the globe, training them and supporting them. And ultrasound has been a very important part of our concept for many years. And when I first joined the company, that wasn't the case. It was actually the low point, you know, if you ever talk to Doug about it, and he and I talked very early on about reinvigorating it and reinventing it. So over the years, as we've trained these people, one thing we encourage them to do is to always send us the cool things they find in the field. So I've been very fortunate to get my ears, if you will, and my eyes on things I might not otherwise be able to do. And that allows us to build our knowledge base, and certainly, you know, we want to share that with everybody else. So the thing I see our folks struggle with the most when it comes to electrical is the analysis part of it. And really that's a technique, and it's not as difficult as it seems once you become familiar with what you should be looking for. The trick really is to do what? To put a face or a picture on a sound. And, you know, it sounds very intimidating when you think about it, pardon the pun, but it really isn't when you get right down to it. Now, there's been a lot of good presentations today and years past, and a lot of focus gets put on decibel level and things like that. Any of you who have been through my presentations in the past know I downplay dB level for the majority of the electrical applications. And there's a reason for that. I mean, it doesn't play a major role as it would with rotating equipment or some mechanical applications. And getting our technicians to understand that can sometimes prove very difficult. So I've been fortunate to have a lot of experience looking at these things over the years and talking to the folks at UE and trying to learn as much as I can. There was going to be some stuff from years past I was going to incorporate as a tutorial type thing today, but I don't think it'll be necessary because the sheer volume of things that have come our way just in the past 12 months allowed me to just present with some new things that I thought you'd be interested in. So I talk about high value assets, saying they demand scrutiny. Well, who determines what's valuable and what's not? I mean, that's really an individual location's decision, but there's a lot of components that if there's a failure or an outage, it's going to impact all aspects of an operation, a building, whatever the case may be. So there's some value to every asset as far as I'm concerned. It depends upon the type of facility you're in. So determining what's critical is on an individualized basis. Hello. I didn't mean to out you, James, sorry. and the question about how important can this be, it's the first tool that I use each and every time for a myriad of reasons. Just for my benefit, show of hands, how many folks are involved in the electrical side of things, so I know. Oh, that's way more than in years past, so that's good to see. Using this regularly on that, show of hands. Lots of questions about what the heck you're hearing and looking at, show of hands. Good. So can you really get any good information from this, and how important is it? It's the first thing I use for a number of reasons. Diagnostics is one, safety is paramount in electrical. Anybody involved in electrical, mainly in North America, but it's growing, knows about arc flash. And I think we're going to, probably have some discussions about arc flash and that. And that's only gaining popularity. If we can do this additional step to protect our technicians before they ever attempt to go into a piece of equipment, that's going to be first and foremost. So it provides us with an alert whether or not something's occurring inside. And when you get right down to it, there's really only going to be about 5 or 6 different things that can and do go wrong in electrical that we're interested in. And I'll talk about those as we go along. But when you think about things like transformers and switch gear and breakers and air switches and things like that, these are the type of assets that when they fail, they take out entire facilities. It's not like a single pole breaker that's feeding a sump pump in a closet somewhere. Oftentimes these feed many different things, and we're going to talk about some of these today and see what we can find out about them. The 5 things that I usually look for are listed right here. We're all familiar with arcing, tracking, and corona. I mean, it's in every spectralizer install, and it gets driven into the ground. But also in electrical, we have to be concerned with mechanical vibrations and the looseness of parts, whether it's a mechanical issue or an electrical type issue that can lead to an ultrasonic emission. And in a lot of cases, it may be more than one of these present causing the issue. All the technologies we got, I heard somebody ask the question about root cause earlier. Does this really provide us with a root cause analysis of anything? No. Everything is symptomatic leading to something else, whether you use an infrared, ultrasound, whatever. It points to some other problem. And if you can stitch those pieces together, you can have a very effective program. So I wrote on this slide, and I probably should have took this out, but I had some stuff planned from before, but it wasn't necessary, so we'll just look at some new stuff that's different. And I like to start with transformers. It doesn't matter what type of facility you're in. This is going to be your first component. And if it goes down, everything is going down, whether you want it to or not. They're probably the most critical component in the majority of the systems we get into. I don't know if any of you have tried to or had to replace these or order them in recent times, but how difficult is that today? Anybody have to order a transformer in their past? How hard is it today? Lead times 10 months? That's good. They're not very common today. They're not sitting on the shelf. Because of that fact, you better maintain them and have the most longevity you can with them. And that lead time is only getting greater. You think about the cost of copper, it's sky high. Very difficult to get on these. It's not going to matter in this case if we're talking about a device that's a dry type or if we're dealing with a pad mount liquid filled transformer. And at the end of the day, these things are exactly the same in their components and their functionality as far as the windings go, the core components and things like that. In the air type, you use convective cooling with the circulation of air. When you get the liquid filled, the oil is the medium for moving this thermal energy around. So for purposes of this discussion, we'll just say they're pretty much the same thing here. The first one I got, did anybody join in on the webinar back in February that I did? A couple of us. This is the same thing for those of you who've already seen it. But I got a customer in Canton, Ohio, and they've been wonderful with this technology. They probably sent me more WAV files than anybody other than Kraft, and Drew knows about that now. So, a guy by the name of Jerry Bennett and Jeff Hinton took this and run with it. You know, they latched onto the training, they practiced, you know, they'd have their extended periods. I'm sure some of you find that you might go months without hearing one single emission, and then all of a sudden you get back-to-back-to-back type emissions. And that's what happened to these guys. And it's difficult because you get complacent, you start to lose faith in the technology. In a lot of cases, maybe it's not being applied in the correct fashion. But we worked with these guys, and they found a whole bunch of stuff here over the past 4 or 5 years. And this is a good one because, believe it or not, it's still ongoing, and it's a couple of years old right now. But a hospital in Canton, Ohio, had hired them to do maintenance on an annual basis. They had completed the first year of service, and they're going back for the second year. And you can imagine with hospitals, there's a lot of assets there that can impact human life, and you don't want them going down, all that good stuff. So very important, high value. They went into here in October of 2011, and this picture I have here is very similar to the unit, it was a unit substation. So a modular enclosure of a switch on the primary, the transformer, and some distribution equipment. And they had been there the previous year and noted no faults whatsoever. And with our world, it's like some of the customers can look at it and say, well, you're not finding anything. What do I need you for? Right? There's a reason that we're not finding anything. It's because we have this ongoing program. And, you know, if we don't find something, that means we're doing our job. Sounds crazy, but really that's what it boils down to. They did what we call our energized services at the beginning of October. And there's a number of different things that we choose to do while the equipment is online, some of which you're probably familiar with, obviously. You know, the ultrasound's always first. We use infrared. You know, we look at voltage and current diagnostics, harmonic content, visual inspection by trained electricians, because really if you're not a qualified person, you shouldn't be in this stuff anyway. And that's a point of contention as well, but that's for another day. So they're doing all these things out there. As I mentioned, it was the second year visit, and on the first year, they had nothing noted of any concern that, you know, would have been alarming, so they let it go and passed everything with flying colors. They got some recordings, and to give you the layout, there was 2 transformers in this vault, or 2 unit substations. And there's a lot of redundancy in these hospitals we go to, and this was no exception. They detected an anomaly on one of the 2 units, but what's the best thing to do if you have identical equipment and there's a question? Comparisons. I mean, we use that with infrared, right? You want to bring that up? Do we use it with voltage and current measurements, resistance, voltage drop, things like that? It only makes sense. Even on the mechanical side, we talk about gearboxes and things like that. But it's here, we're going to compare them. And because we had 2 identical units that were running at, you'll see, you know, very similar loads, what would you reasonably expect to hear related to an ultrasonic emission on a transformer? Anybody? Nothing. You know, you may, depending on the load levels, the harmonic content, the combination of that, there may be higher or lower audible levels of hum. And everybody knows the old joke, why is a transformer hum? Doesn't know the words. So that may or may not be there. It depends on a lot of variables and parameters. But ideally, it should be uniform in nature between the 3 coils. There shouldn't be notable differences. And I've got this one here. This is just a sample of what they heard on the suspect transformer. So the A-phase coil, if you wouldn't mind clicking that. But there's that faint 60 cycle hum that you'd be accustomed to. But other than that, is there any, you know, anything on top of the normal stuff that might raise a red flag? It's pretty good tonal quality. Now, if we go to the B-phase coil, maybe it's a little different. my fault it's that long? Because I tell them make a lengthy recording when it comes to certain devices. I mean, is there a uniform amount of time that a technician or an ultraprobe user should make a recording? Not really. It depends on your specimen, doesn't it? And, you know, there's certain changes or, you know, the cyclical nature of some of these loads, continuous nature. Maybe a 5-second recording is okay on some equipment, but particularly with transformers and that, we typically ask our guys to record 20 to 30 seconds because there's minor things that can and do occur that you're not going to pick up in 5 seconds. I had an example of that a couple years ago in a paper from a unit in Australia. You know, just very early stages of breakdown in a liquid-filled tranny that there was 2 discharges. It was arcing. I mean, starting to break down. And it took about 20 seconds to capture them 2 discharges. In this case, loud and annoying, no doubt. Now you can hear that hum a little better. But nothing really out of the ordinary, agreed? So just using comparisons, what would you say about that if you were out in the field and you came across this? Something's going on in that B-phase coil because it was really annoying. Now, I told you I had this, you know, they had the sister unit sitting next to it, an identical unit. Does it make sense to go ahead and take a listen there? Sure. We'll do the same thing. It may be more pleasant on your ears. Again, you have a low-level hum. And we'll just cycle through each one of these. That one's even quieter yet. That sounds a little better, doesn't it? Now, this is on a dry type transformer, so simply using the airborne attachment in this case was adequate. What if we had a liquid-filled unit? Would that be the attachment of choice? You'd want to switch to what? I'm using the magnet, especially for longer recordings. Everybody knows how you can move that contact module. You get false positives on the spectrums. So try and avoid that. But anyway, you can never go based on a sound. Yeah, I'm sorry, go ahead.
Did you ever compare the current, the load on the...
I did. I'm getting to that coming up. I just wanted you to hear the recordings that raise the attention. So anytime there is some type of anomaly, you got to analyze this. I mean, if anybody's using infrared, would you make a determination based on just a picture? If you do, you're making a mistake. I'll just say that. It's no different with ultrasound. Everything has a footprint. I actually heard that earlier, so I was glad to hear it. And the stuff we cataloged earlier is no exception. Every one of those 5 things has some footprint that is predictable, repeatable, and easily identified using the right tools and setting this tool up in the correct fashion. Because there's a right way and a wrong way to use spectralizer for the electrical applications. Up here, we know there's a qualitative difference in the sound of the recordings. But this is looking at the frequency spectrum for both B-phase coils on the suspect unit and the good unit. Just, I mean, in general terms, does there appear to be a difference? What can you pick out from there that stands out? The amplitude of where the harmonic frequencies are and the amount of noise in between each one of those. Okay, there's some similarities here, and the one in white is the one you're all familiar with out of the library provided to you of tracking. Because Roger, you said it was tracking, didn't you? But if we look at that compared to the red one up there, it doesn't have the same faults, which means maybe it's not tracking. And comparing the two, just here, we always tell our guys, if you use just the FFT, you're going to miss things. What I talked about a couple of years ago is this tool tells me 2 things. It tells me, number 1, if it's some type of fault, and number 2, if it's electrical in nature or not. I can rule out electrical or non-electrical type issues using, it doesn't tell me what it is, it tells me the nature of it. So that's what I'm using here. The frequency noise in between tells me something related to electrical is there, but it doesn't have the spectrum I would expect if it was tracking or arcing. It's something different in this case. Looking at the time domain, this could be a little tricky here if you think about it, because it does have a footprint, or what I call a footprint of a tracking anomaly. And the way we characterize that or put a picture on it is what? We have variation throughout the recording in the amplitude of these excursions, the center line here, I mean, for lack of better words. And you also have differences in the spacing, meaning time. And if you think about tracking and you relate that to an electrical sine wave, you know, without getting too deep, if you're on a 60 hertz system, one electrical cycle is a very predictable, repeatable time base of 16 milliseconds. And when you have discharges of energy along insulators, there is no pattern to when that occurs relative to a sine wave. So the timing changes with this tool on tracking event. It's not like that with some other events, but at least with tracking, it is. So you will see differences there. So this is the one that's suspect, and here's the comparative coil. Is there a qualitative difference here? I mean, it's night and day, isn't it? That doesn't tell me, you know, tell us what's wrong. And you got to know Jerry and Jeff from Ohio, they're very excitable. So they send me these things, and, you know, they're real anxious to kind of get some guidance on this. And I send it back to them after a little while or whatever, and actually end up going over it. I'll get to that part of the story. Mr. Goodman turned me on to this one here, another tip and technique I learned from him about slicing up the time domain, because we're dealing with short time periods in AC electrical systems. You can get a more defined view of what's going on with these things. And looking at the suspect coil, although there are differences in the amplitudes of these, what I call excursions, the timing appears to be pretty consistent throughout this recording here. Only some variations, which I attribute to possibly changes in load. Couldn't verify that for sure, but that's what I suspected was going on. On the FFT, I say the fault frequencies were not on the 60 hertz cursor. Everything we've learned about electrical fault, tracking, and corona, what are we looking for as far as these harmonic frequencies? The base operating frequency. So if I'm on a 60 hertz system, I'm looking for multiples of 60 for it to be some type of electrical type anomaly. Looking at this, there's really nothing hitting on 60, agreed? So there's a shift in where this is peaking, and that's got to be caused by something. Even defining it a little more, I hate pointing at the screen, but there's a slight 30 hertz peak on the bottom of this. Now that's unusual. I thought it was unusual because I'm used to seeing them on the top. But what do we know about a 30 hertz frequency on a 60 hertz? Sorry? Something, it could be vibration, but it's not electrical, it'll be mechanical in nature. So that definitely raised an eyebrow. And, you know, it started us down a different road of it could be this, it could be that. To give you some ideas about the unit we're talking about, they're listed here. This is a unit Square D. It's a 2000 kVA transformer. It's got a 12470 kV primary side, 48277 secondary. It's 5 years old. And the unit that's sitting next to it is also 5 years old. The manufacture date was the end of 2004. Now, how long are transformers designed to have a useful service life? Does anybody know? Actually, it's about 30 years, 30 to 35 years with what? Proper maintenance. That's a key thing. If you just put it in service and let it go, don't expect to get 30 years out of it. But if it's properly installed and maintained, you can get 30 to 35 years out of it. This is 5 years old. Should there be any type of problems, knowing there's a program in place? Nothing. But there's obviously something going on here. You asked about the load levels, and those are listed here on the bottom. This is the good unit right here, and the suspect, or what I call the bad units, on the right-hand side. Fairly balanced loads. The full load rating on this is 2,400 amps. And on the good transformer, about 830 on A and B phase, a little higher, some imbalance on the C phase at 890 amps. Well, how is this much different on the suspect unit if I have 870, 877 amps, and 960? Is that fairly balanced between the two units? I mean, there's some difference, but it's pretty close. So knowing you have relatively similar operating conditions, should the units both look the same thermally and sound the same ultrasonically? That's what I thought too. So there's something out of the ordinary. That's your parameters. Another good indicator was the first, I'll throw the infrared image up. I actually had to get on Jerry about this one because the one on the right is a suspect coil, and he did a boo-boo on this one. Can anybody point it out?
Oh, he's out of range.
He's out of range. So, I obviously said, well, I can't help you on that one. And, the indicator's what? The saturation. But what I thought was interesting about it, this is on the good coil. It's a little hot, but that's a core. Are the transformer cores typically higher in temperature than anything else on a transformer? What's the reason for that? The magnetic fields. We're talking about the induction going on within there that generates a lot of energy. But, this one here was certainly higher. It exceeded the dynamic range of the camera. And the other thing that was suspect to me, even though the range was exceeded from a temperature measurement standpoint, I don't even think about temperature at first. I'm looking at patterns. Rick will tell you that. Right? I talk thermal patterns when it comes to electrical because it allows me to identify the origin of the thermal energy and the direction of flow. And that's important when you're trying to find the cause of these symptoms. In this particular case, it seems as though the origin of that thermal energy is somewhere down inside the core. And that can be problematic because the windings are wrapped around the core. That happens to be the primary side on the inside, and the only thing separating them is that varnish insulation on the windings. So if that starts to deteriorate and degrade, you could have a big problem from a operation standpoint and or arc flash standpoint. So with this evidence, we convinced the customer, you better take an outage. Due to the redundancies, you're able to shut this down, with a little bit of coordination. It's a nightmare to coordinate things in a hospital or a data center or a lot of places, but it can be done. So we convinced them to shut it down to let us do some other testing on there to find out if this anomaly has caused some type of electrical damage. Now, we agreed a moment ago that looking at the FFT in the time domain, this is not some type of electrical fault in nature, right? It's something mechanical, and that's undetermined at this point. But can mechanical things that go wrong in a unit like this actually cause an electrical failure? They sure can. And that's the concern here, especially with a 5-year-old unit. So we're going to be looking at things like this. And those of you involved in the electrical field, you know what these are. Those of you who are not, the insulation resistance testing allows us to determine the health and integrity of the insulating system. You apply a voltage to it, it stresses that material to determine whether or not it can withstand those higher voltages. And particularly with transformers, the inrush currents on them things, when you bring them back online, are very high. So the dielectric strength of that, not just the conductors, but the winding insulation itself better be good. Heating effects will break that down. Something vibrating on it and chafing it will break that material down. This test is a very good indicator of whether or not that's happening. Winding resistance is just to compare between the 3 coils on both the primary and the secondary phase. Do you have balanced impedances on the coil? If your impedances are not matched, how does that impact the operation of this device? Anybody know? Sorry? You'll lose your power factor for sure because the voltages and the currents become unbalanced. That doesn't, that can throw the phase angles off. That can also have a ripple effect all the way downstream into the system, and it gets exacerbated as it goes through all the components. So you get uneven heating and cooling, it just leads to a myriad of really nasty problems. The other one I got on here is called turns ratio testing. Has anybody ever heard of that? Good. Those of you who have not. A turns ratio test is the only test available to us to tell us a couple of things, but most importantly, are there turn-to-turn shorts within the windings? If you're familiar with the construction of a transformer, you know, you see them windings in there, and every one of them coils of wire are electrically isolated from the next one. They're wrapped in a varnish and baked in an oven and things like that. So they don't touch each other as they're wrapped and stacked. If those things short out one turn to the next, that's going to have an impact on the balance for the voltage and current again, because you're altering what's called the ratio. How many turns of wire do you have in the primary compared to the secondary? And that's by nature of its design, that's what a transformer does. You apply a certain voltage and it transforms it to something either higher or lower. And that's based upon how many turns you have in the primary side compared to how many turns in the secondary. A lot of transformers will have more than one tap on the primary side to allow you to apply different levels of voltage on the primary side and still maintain the same secondary voltage. That can be changed without ever messing with the taps, simply by getting turn-to-turn shorts. The other thing that can identify is problems within the core of the transformer related to the laminations and the bond of those laminates and things like that. And the last one here is called a power factor or dissipation factor. That's just a measure of the watt loss through the insulating systems on higher voltages between the resistive and reactive power elements. So these are measures that can be done to tell us how healthy is this unit. And knowing that things like we just heard can cause problems, it's an important thing to know. They hired a third-party testing organization, even though they're perfectly capable of performing these tests themselves. They brought somebody in from the outside. Why would they take that step and employ a third-party testing company?
More eyes, the better.
There you go. More eyes, the better. And, you know, it's not biased, if you will. They are the ones that reported this could be a problem. So if there really was something to this, they wanted somebody else saying it. And quite frankly, they wanted to validate what they were thinking as well. So the winding resistance test, all you're looking here on this test is balance between the coils. They should be almost identical if it's constructed correctly. And they were within the 1% tolerance based on this data right here. So everything looked good there. This here indicates the insulation resistance test. And as I mentioned, this tells us how well can the insulating system contain the stresses. And remember, on the primary side is 12,000 volts, secondary is 480. And what you look for from a maintenance testing standpoint here is you apply a voltage, ideally that's above the rating of the insulation, for a period of time, and gauge those results against what's called a polarization index. And essentially what you're doing is the test voltage is applied for a 10-minute period, and the device is measuring leakage currents. When you first apply the leakage currents, the resistance is the test voltage, the resistance is very low because there's a lot of leakage currents, and they eventually seal off. It's a charging current on large equipment. It takes some time to stabilize. So you'll typically have lower values of resistance that climbs over this 10-minute period. And determine what the polarization index is, you simply take the 10-minute measurement divided by the 1-minute measurement, and the higher the better. You know, if it's a flat line or it goes down, there's a problem. These results here are self-explanatory. This is looking at the primary side. 10,000 volts was applied. If it was me, I'd have went a little higher, but hey, you get what you get. You see the 1-minute reading started out at like 330 megohms, and they build up over 1 gigaohm there. And when you calculate them, the PIs are over 5, which is a very good indicator. That tells me that there's no damage to the insulating system at this point, which was good. Secondary side, same thing, lower test voltage, because the voltage on the secondary is lower as well. The turns ratio measurements. Remember I said this looks for turn-to-turn shorts. It's the only test that can tell us that. You may or may not get some indications that's occurring with an infrared camera or an ultra probe, but you can never be sure unless you run this test. The tolerances on this are 0.5%. So when you apply this test, you calculate what the ideal ratio should be and gauge the results against that, plus each measurement on each coil. And they all have to be within 1/2 of 1%. So the tolerances are very tight for a reason of the voltage and current balance I mentioned earlier. This was right on, so no damage there. And finally, this one shows the results of that dissipation factor, the difference between the losses of the resistive and reactive power elements, and we see that typically as heat. So it has to do with the efficiency of which the device runs and how well the insulating system is. Now, back to the subject at hand here with the ultrasound. Sorry about that long-winded explanation. This is a visual image of the area of concern here. And what you're looking at, this is that B-phase coil, and there's them windings I told you were insulated and isolated from each other. You can see the varnish on it and all the shims in between them. And this piece going down here is the vertical core piece. It goes down inside this winding, and the outer part of this comprises what we call the secondary. The internal part of it comprises the primary windings. Up here is the vertical piece that's common to all three of them. Those are joined together in the manufacturing process. I mean, from a visual inspection standpoint, what do you think about the condition of this unit and considering where it's located? It's a little dusty, but other than that, for 5 years old, it looks pretty darn good. There's no evidence here that the insulating system might have been overheating, right? The core doesn't look at this point like it's overheating. But then again, you know, we exceeded the dynamic range of that infrared camera, but so what? The cores run hot. I'm not worried about that. That's good news for the customer, isn't it? Or is it? No, everything hasn't been revealed yet. We got to get to the root of this problem. So I say the answer is yes and no. And, you know, the visual inspection is going to give us something a lot more telling as we get into this, right in this area. Do you see this guy is pulling back the varnish? I'm going to go back to the previous image right here. Everybody can see this varnish paper up here. It's kind of separating the busing system from the core. And what he's doing is he's grabbing this piece and pulling it back to inspect the core. All right, and that's what you're looking at right here. So once we get these apart, these cores are constructed with this vertical piece, 3 horizontal pieces, and a bottom horizontal piece. And it's all joined and welded together, mitered for a good fit. You know, the steel keeps it all together in there, as you can see up here. The welded part right here is what does the joining mechanically, and you have the vertical clamping steel down here, the horizontal clamping steel in this area right here. And behind this paper was the source of the highest emission. And remember the thermal energy coming from inside the horizontal piece there. But if you look closely, it's a little hard to tell because it's dark. I don't know if you can turn these lights out, but this image is dark. These two pieces between the horizontal and vertical part are perfectly flush. So can everybody see that okay? It's a little hard to see, isn't it? But, you know, if it was a little darker with these lights, you'd see these are extremely flat. You could run your hand across it, feel no elevation differences. That's the way it should be. That's the way it's designed to go together. When we look at the coil in question, it's a totally different story, and I think you can see this a little better. But this horizontal piece right here, where it meets the vertical piece, there's the clamping still here. There's an elevation difference of almost 1/4 inch between those two pieces. So when it came together, instead of being nice and flush on this joint, it was offset, and it went out like that. Well, that's interesting, because what did we say the core's job is? What's the purpose of the iron core here? Concentrate the magnetic fields. And it has to be, you know, put together the correct way in order to do that efficiently. All right? And that's exactly where the highest decibel level on the recording was taken. Well, that sounds strange because didn't I start this thing off saying I don't care about decibel level? Let me qualify that. Decibel level tells me one thing on these types of anomalies. It tells me how close I am to the source. Just because it's 11 dB here or 20 dB here, that doesn't mean anything to me from a severity criteria standpoint. It tells me how close or how far away I am from the source of that emission. It happened to be highest here. Because it's so directional, it allows me to isolate down the general area where it's coming from. That tells me where to focus my efforts on the shutdown, doesn't it? So digging into that a little deeper, you can see on this core piece right here, what does that look like to you? It's burnt. That's a darkened area, and on these are all pieces of iron that are laminated and bonded together. I don't know if anybody knows how a core is put together, but it's a whole bunch of pieces of iron that are kind of laminated, they're bonded together, and they're varnished and baked. And that varnish, you know, it's a pretty nice finish when it's on there. You have clamping bolts that go through there to hold it together nice and tight. And those laminates make sure that the flux lines are concentrated in the proper fashion. But that heating up like this, well, we saw that with the camera. I expect some visual evidence of heating, wouldn't you? You saw the infrared image. We get into it a little deeper, though. Now the root of why we were hearing is becoming more evident here, what we heard in the ultraprobe. You know, there were signs, we heard it with our ears, but looking right here, this is a separation in those laminates that, for perspective's sake, the guy that was out there could stick a flathead screwdriver down into the slot. And this area right here is supposed to be bonded with that steel. Now, these laminates have now separated, haven't they? So you put thin pieces of metal into a magnetic field, what do you think is going to happen to it? It's going to vibrate. It's also going to produce what? Heat, noise, you name it. It's not going to be very efficient. It's going to shorten the life, and it's going to continue to delaminate. That's a problem when it comes to those insulators, when you think about it. So this is now looking more and more like the root cause of why we heard what we did. Even going in further, you can see the first part right here where it's separated. There's separations into the core toward the high side or the 12,000 volt side. And this, immediately it looks like what? If the unit's only 5 years old and this is going on, what do you suspect? It's a defect. But manufacturers never have defects, do they? They don't want to, and this one didn't either. Remember I said Square D manufactured this. And I was on my way somewhere to teach a class one time. I was at the airport in Pittsburgh, and I get a call from my contractor, and he says, do you have time to do a conference call with Square D about this transformer? Talking about this one here. And I said, sure. So he arranges this, and they get their engineers on the phone. And we're sitting here discussing, you know, our process and our kind of conclusion about what's going on here. And when I mentioned to him that this all came about as a result of using the ultraprobe, his question to me was, what's ultrasonic testing? I'm like, really? You know, you're the one that's got the sheepskin, not me. But in all, they'd never heard of it. He's like, is that like partial discharge testing? You know, if you're in electrical, you probably heard about PD testing. That's a different technology. It utilizes different frequencies, different application altogether. But I had to sit here for about 45 minutes and just kind of explain what the ultraprobe did to him so he could have an understanding of using acoustical detection and how it tied into this. Well, you know how Square D reacted. They didn't want to hear it. Couldn't be their unit, right? So they come out. They organize this shutdown, another shutdown, to bring Square D and their engineers out because they're fighting this. And the reason they're fighting this is how many of these units you think are floating around out there in the world. And if this one's defective, odds are there's probably a few more, and they don't like that prospect. And I'm not bad-mouthing Square D, so please don't take it that way. Looking at the top of the core, The evidence of what's happening with, the heating effects is even more evident on the varnish. When this stuff bubbles up and bursts and things like that, it's it's higher than normal temperatures. You don't want to see this on the core varnish. That was completely encapsulating the entire core on this unit at 5 years old. Because this miter joint right here, and they these core pieces so they fit nice and snug. They'll bond them, they'll varnish them, like I said, bolt them together, bake them in the oven to ensure there's a good bond, and because they can't separate. But it says here that the miter joint connects the center phase of the horizontal laminates is no longer connected properly because that B phase is bowing out. And it's hard to see in these pictures, but it was literally offset by about a 1/4 inch. It was horrible. And unless you pulled back the varnish shield, you never saw it. But it sure, indicated it with the probe, so that was a good thing. With this thing not being bonded properly, now those magnetic flux lines are interrupted and disturbed. And it's going to have to work a lot harder to maintain that or concentrate them lines of flux, which is going to create what? Two things. What was it? Arcing. Well, not arcing yet. It could. In this case, it didn't. But it's going to create thermal energy. We saw that because the flux density is not going to be what it needs to be to do its job. But it's also going to create ultrasound, which it did. It was causing these laminates to vibrate. Remember on the FFT, I said there's not 60 hertz harmonics present on this spectrum, was there? There was a shift in the frequencies. And it's all about that vibration. Slight 30 hertz, not as pronounced as I'm used to seeing, but it led me to believe we had something mechanical. Hadn't caused an electrical fault yet, but can it in this case. Eventually it's going to break it down. You'll see the winding insulation deteriorate, and it's going to fail them tests we talked about earlier. So, bringing this all to light, giving Square D the third-party independent testing results and recommendations, what do you think their response was? It's not our fault. It's not our fault. And I'm sitting here in my own mind saying, aren't you the ones that made this? Manufactured it? Yeah, it is your fault. There's litigation right now. They're fighting back and forth between the hospitals. It's a high-dollar item, right? And it's a critical care unit building that this transformer is installed in. And remember, there's another unit exactly like it, sitting next to it. We haven't got to that one yet. But it's obviously a manufacturer's defect. And I'll let you know when I find out the litigation. But you look at the sister unit here. This is that same piece of steel on the superstructure. And if you see this cracking, any idea what that's from? Well, not mechanical yet, but this is the same separation of the laminates that we saw back here on this one. Remember this big gap right there? And then it's in here, and it's over here, and it's moving deeper into the core. Well, this unit right here is already exhibiting the same signs. So over time, what do you think the end result's going to be? Same thing. They, from my understanding, they had taken this unit out of service as well and verified that the miter joint was not lined up properly as well. And it's a real simple fix. It really is. You take the unit out of service, you drill a new hole, break the weld, line it up, and re-weld it. It can be fixed right in place. And it's being fought for reasons I do not know. But this is ongoing. Eventually, it's going to have the same delamination in the middle, thermal effects, and I believe the ultrasound, because we didn't have any at the time of recording. So a whole year goes by with this bickering back and forth between, the customer and Square D and the contractor, and it's just, stalling for time. Going back 1 year later, that core temperature is still increasing. It's still coming from inside. And when you go back for another service, what do you think you want to do if you had something the previous year? Let's compare it again. So do you remember the quality? Well, you remember the annoying sound we heard of that B-phase coil, don't you? Let's see what it sounded like a year later. Want to help me out there, Mike? Too, doesn't it? Sounds like what? Yeah? Or an engraver. So there were some early pops in there too if you listen real close. This thing's already starting to deteriorate. So they need to act on it. It's not resolved yet. And I'm really curious to see this one through. But it all started with an emission. It was all related to a mechanical issue that's going to lead to some type of fault electrically on the insulating system. And, you know, it may not have been picked up otherwise. Yes, sir?
What's their worst case scenario if this thing does run fast? It's going to call fire?
Well, who knows? I mean, it's in a vault, but what it's feeding is more of a concern because there's many different buildings on the campuses, and this is one of the critical care facilities.
I'm just thinking, you know, the insurance company don't know about that.
They're involved. You're absolutely right. And, you know, I mean, I don't know all the details because of what's going on as far as the legalities on this, but it's a very pressing issue to the customer. You know, the hospital wants it fixed. And they got their, you know, legal eagles involved just like everybody else. But the last time I talked to them about this was probably about 3 months ago. And they're monitoring this more frequently now to try and trend any degradation. Not with the de-energized maintenance, but with the energized stuff. And it's getting worse. So I was glad they found it, and you know, this will help make them shine, if you will. These guys have found many things. I did one several years back on Kraft Foods with a 12470 switch that did have destructive corona going on, and that thing blows up. It's taking out the whole mezzanine. This thing here might take the other unit out. There goes your redundancy. So to the customer, it's a pressing issue. To the supplier, I think they want to try and forget it rather than fix it. And they could make it right, but they haven't. Okay? Is there any questions on that? Yes, sir.
Did you ever run that 30 cycle vibration ground?
On?
There was a 30 cycle harmonic.
Right. There was. It was a very small one. I'm used to seeing them on the other side of the FFT, but it was enough to say, hey, that looks different. Yeah, it doesn't belong on this. And the fact everything else was shifted off the 60 hertz harmonics, I mean, like I said, the FFT tells me is it electrical or not. The fact it was not on the 60 hertz harmonics, it's not an electrical issue yet. That's how I looked at it. Okay? Anybody else on that one?
Sorry, because you're moving the next one, sorry, I thought you continue on slightly. Transformers, you take the sound from this transformer, you know, typically dry type transformers, they are enclosed. I saw the pictures early on, you can actually see some little gaps, but normally it's in the top or the bottom, there's a little bit of race. How do you, what's your SOP for taking the three coils? Do you actually take them approximately where the position needs to be the sound, or you take a lever up and point it down?
It depends on the transformer, but typically you have convection air vents on the dry units. So it's easy to use the airborne and do a very panoramic scan of the entire unit on the top and the bottom. A lot of the units I've dealt with. Now, if not, they've obviously got to be opened up, which can be dangerous since you're dealing with a 12,000 volt primary here.
Probably not possible, because usually it's trip switch. It was just curious to see. Yeah. Yep. You may not get the exact okay.
Well, the other alternative, keep in mind, we got the contact module or the magnetic mount. That can and has been used as well. In this case, it was airborne because it did have convection vents. And, you know, Jerry's a pretty tall guy. He's, believe it or not, he's taller than Ugo, so he could reach up there and get it. I had to get him. He knows I love him. All right, yes, sir, another question.
Yeah, do you have any kind of data at all that help you predict the amount of time you got left?
Boy, there's the $1,000,000 question. I wish I did, but we don't. Yeah, it's so many variables to consider. Yes, sir. It is. That's really what it boils down to. Oh, sorry. 1 second, sir. What do you mean mess the harmonics up?
They end up getting dirty power going down through there, and it ends up messing up. I mean, I know if it's a hospital.
Yeah, it could cause some noise on the line, but related to harmonics, that's actually a product of the loads within the facility that produce them and send them back toward the transformer. So you may get some electrical noise on the line, which is bad for the sensitive loads, but it's actually those sensitive loads that produce the harmonics that return on the system. Does that make sense? Yes, sir?
Would that be seen in, say, an electrical motor that's closest to the source?
If it's on a drive, possibly. You know, you think about a variable speed drive, it's basically a rectifier, right? And that rectifier produces harmonics that go back on the system. So the closer you get to these loads, the higher the levels of harmonics you'll see. And it's a similar concept in the FFT, it's multiples of 60. And then depending on the technology you're using, diodes, SCRs, IGBTs will determine what frequencies are produced. Is it single phase, is it three phase?